Hello there, and welcome to the Sleepy Explorer. I'm glad you found your way here tonight. This is your cozy corner of the universe, a place where science leans back in its chair, curiosity puts on pajamas, and the vast cosmos shrinks just enough to fit comfortably beside you. Tonight, we're drifting into one of the most mysterious dances the universe has ever choreographed. The slow, inevitable pull of two black holes toward one another. It might sound like the start of a cosmic romance, two invisible giants drawn together across unimaginable distances. Their meeting is written not in poetry, but in gravity, yet it has all the drama of a love story that ends in one breathtaking union. Of course, if you tried to sneak too close for a front row seat, reality would remind you why that's a bad idea. Before you could even whisper, "Ah, young love," you'd be stretched out like spaghetti, thinned to the point of vanishing. Not quite the kind of dinner date you'd want to be part of. So, before we settle in, take a moment to like the video and subscribe, but only if you truly find these quiet journeys relaxing and meaningful. And since this sleepy little community is scattered across the planet like stars in a galaxy, I'd love to know where you're listening from and what time it is for you right now. It's always a joy to see how far these calm explorations reach. Now, dim the lights, let your muscles unclench, maybe turn on a fan for that soft background hum, and let's drift into tonight's story together. Imagine yourself floating beyond the noise of Earth, past the warm glow of familiar stars, until all that remains is the silence of deep space. There, in the endless dark, two black holes wander, each invisible, each a silent master of gravity. You hover at a safe distance, watching without being watched, like a dreamer inside someone else's dream. The first black hole is enormous, millions of times heavier than our Sun, a collapsed core of a once mighty star. Its event horizon, the no-return border where light itself gives up, is smooth and perfect, a sphere of nothing that somehow feels heavier than everything. Across the void, another waits. Smaller perhaps, but no less strange. Each is patient, as black holes tend to be. After all, time bends near their edges, so waiting 1 billion years is about as stressful to them as waiting for your tea to cool is for you. At first glance, you'd think nothing would ever bring them together. Space, after all, is not crowded. It's not even empty in the way your room feels empty when you've tidied it. It's so much emptier than that. Galaxies drift like islands in a dark sea, and inside those galaxies, stars are separated by gulfs so large that if one star were the size of a marble on your desk, its nearest neighbour would be another marble sitting on someone else's desk a continent away. Black holes are even rarer than stars. And yet, sometimes, in a cosmic coincidence so rare it feels scripted, two find themselves on intersecting paths. The pull begins quietly. Nothing flashes, nothing sparks, no fireworks, no dramatic background music, just gravity, gentle at first, then stronger with each passing epoch. Like two dancers who begin far apart on a silent stage, they circle one another in slow, patient arcs. You notice how the surrounding stars wobble, as though space itself is breathing differently here. You can almost hear the rhythm, a pulse too low for human ears but steady enough to be real. Scientists tell us these movements stir space-time itself, sending out ripples, gravitational waves that pass invisibly through you right now, even as you listen. You don't feel them, of course. They're so faint that even when two black holes collide, the tremor they send through Earth is smaller than the width of a proton. And yet, with the right instruments, we can hear them. But you don't need instruments here. You can imagine it the whisper of gravity, like the softest drumbeat under the silence of space. It's not a song you'd dance to, unless you consider drifting for billions of years a kind of dance. Still, it's a rhythm you can trust. The two giants are bound now. They can't escape one another's pull any more than you can escape the slow rocking of your breath as you lie in bed. You drift closer, and you wonder, what are black holes really? Are they holes? Are they objects? Or are they just boundaries, places where the rules of reality decide they've had enough? Scientists still argue whether a black hole is best described as a point of infinite density, or if it hides some yet unknown state of matter we can't imagine. To you, though, it doesn't really matter. What you see or don't see is compelling enough. A place where everything goes in and nothing comes back out. A place where time slows, bends, stretches, and then, depending on your point of view, perhaps even ends. The two continue circling, closer with each sweep, their paths spiraling tighter. You feel a kind of sleepy reassurance in their patience. The universe is in no rush, neither are they. If it takes 1 billion years, then it takes 1 billion years. Time for black holes is not a straight line. It's something more like honey, thick and slow, stretching endlessly. And you, watching them, feel that honey-like flow seeping into your own awareness. Seconds lengthen. Your mind drifts. You feel yourself loosening, like you've been caught in a gravity of your own. There's something comforting about the inevitability of it all. These two will meet, someday. Nothing can stop it. And while you might not be here to see it, someone or something will. Perhaps a civilization far in the future, listening from their quiet world, wondering if they too might merge with the infinite one day. As you drift alongside these two invisible giants, you sense that this story is not just theirs. It's the story of the cosmos itself. Quiet beginnings, long, patient dances. Moments of sudden, dramatic change, then echoes that last long after the moment itself has passed. You float, listening to their silence, until the idea of time itself feels less urgent, less sharp. You can let go. After all, if black holes can wait 1 billion years to finish their dance, you can let yourself relax for a few hours tonight. The universe will still be here in the morning. You float closer, letting the silence of space wrap around you like a blanket, and your gaze settles on one of these strange giants. To understand what it means for two black holes to merge, you have to understand what a black hole is in the first place. The phrase itself is misleading, isn't it? Hole suggests emptiness, a gap, maybe something like the hole in your sock. But this is no hollow absence, it's the densest something that nature has ever produced. It's more accurate to think of it as matter collapsed beyond recognition, squeezed until even the concept of surface stops making sense. Imagine a star much larger than our Sunday. It spends millions of years burning fuel, fusing atoms together, fighting against its own gravity with light and heat. But eventually, the fuel runs out. And when it does, the star loses its fight against gravity. The core collapses, crushing atoms, breaking down protons, forcing matter into a state so compressed that no known force can resist it. For smaller stars, this collapse halts, perhaps leaving behind a neutron star, itself unimaginably dense. But for the biggest stars, even that fails. Gravity wins absolutely, and the result is a black hole. What does that mean in practice? Well, if you replaced Earth with a black hole of the same mass, nothing about our orbit around the Sun would change. Earth would still circle serenely, as if nothing had happened. That's the strange thing about black holes. From a distance, they behave just like any other mass. The weirdness only begins when you get too close, when you cross that invisible border called the event horizon. That's the edge where light itself gives up trying to leave. It's not a wall. It's more like a silent checkpoint, beyond which the rules you thought you knew unravel. Scientists describe the black hole with startling simplicity. Just 3 numbers: its mass, its spin, and its electric charge. That's it. No texture, no surface detail, no scars to show whether it was born from a supernova or grew fat by swallowing stars. John Wheeler, the physicist who popularized the term black hole, put it plainly: black holes have no hair. They reveal nothing personal, nothing unique. To you, though, as you hover here in the quiet dark, they feel anything but bland. You try to picture the center, the singularity. Mathematically, it's a point of infinite density, where gravity is so intense that space-time itself folds into a place beyond comprehension. But whether that's a real thing or just a placeholder for our ignorance is still debated. Scientists still argue whether the singularity truly exists, or if quantum effects we don't yet understand prevent infinite anything from happening. For now, it's a mystery wrapped in equations. You don't see the singularity, of course you never could. All you see is the horizon, the edge where light vanishes. And here's where the strangeness intensifies. To you, watching from afar, anything falling in seems to slow down as it approaches the horizon. Time itself stretches, so that in your view, the falling object never quite crosses over. It freezes, fading, redshifting into invisibility. But if you were the object falling in, you'd have no such hesitation. You'd cross the horizon in seconds, never noticing the difference until the spaghettification begins. Yes, That's the real term scientists use. Your feet, closer to the hole, feel a stronger pull than your head. The stretch grows, violent and unrelenting, until you're pulled thin as a noodle. Not the coziest image to drift off with, but hey, at least you'd go down in physics textbooks as astronaut pasta. And yet, despite the terror of it, there's a beauty too. The event horizon is flawless, like a perfect circle drawn on the fabric of space. The blackness is not empty. It's saturated with gravity, thick with mystery. Surrounding it, matter falling inward, can form an accretion disk, a whirl of gas and dust heated until it glows brighter than entire galaxies. Some black holes even launch jets of plasma thousands of light years long, like cosmic fire hoses spraying energy into space. How something that devours light can also spew energy outward is one of those paradoxes scientists adore. From here, you can see the two black holes circling each other again, each one defined only by its horizon, each one erasing the story of how it was born. They are, in the simplest terms, just gravity concentrated to an impossible degree, but to you, they are characters silent, patient, enigmatic. You can't help but wonder if they know each other, if knowing means anything when you're a singularity wrapped in space-time. You close your eyes, though, in space. Eyes open or closed makes little difference, and you imagine the pull. Black holes are often thought of as cosmic vacuum cleaners, sucking everything in. But that's not quite right. They're more like traps, passive, waiting. You have to wander too close for them to matter. A star drifting near may be shredded, a gas cloud torn apart. But if you're cautious, if you keep your orbit steady and wide, you can linger here forever, watching their slow circling dance. The idea that nothing escapes sounds absolute, but even here, exceptions whisper through. Quantum mechanics suggests that black holes might not be eternal. They may slowly leak energy, radiating faint heat, shrinking over trillions of years. This idea, Hawking radiation, is still debated, still unconfirmed. But if true, it means black holes aren't forever. They die, eventually. Even the darkest objects fade. That thought is strangely comforting, isn't it? Nothing lasts forever, not even gravity's most powerful fortress. And so you hover, feeling their presence. These creatures that are not creatures. They are wholes, and yet they are things. They are nothing, and yet they are everything. They are the universe's most efficient secret keepers. Every particle that falls in becomes part of their silence, its information locked away, perhaps forever. And scientists still argue whether that information is lost for good, or whether the universe, mischievous as ever, hides it somewhere in the physics we've yet to uncover. As the two black holes continue their approach, you begin to see why their merger matters so much. It's not just about gravity, it's about the ultimate test of what reality is made of. Every time black holes collide, space-time itself shakes, sending clues across the universe. To listen to them is to listen to the universe's own heartbeat. And so you settle deeper into your pillow, the image of those two horizons etched softly in your imagination. Two circles of silence, approaching slowly. You let your breath match their pace, steady, inevitable, calm. The story is just beginning, and the universe has all the time in the world to tell it. You notice it first not as a sudden pull, but as a gentle persuasion, the kind of nudge you feel when two people lean in close at a crowded table, not because they have to, but because gravity, real or metaphorical, wants them together. Out here, though, gravity isn't a suggestion. It's the absolute ruler, and it's been calling the tune since the beginning of time. Two black holes circling each other don't rush in like lovers in a romance novel. They play the long game. Their dance begins light years apart, when their mutual pull first tugs ever so slightly at their paths. You could be drifting millions of kilometers away and still sense it, a faint acceleration, an invisible thread tightening. If you had a cosmic violin, this is the note you'd hear, low, deep, and patient. Gravity is quirky that way. It's the weakest of the fundamental forces, so weak you can pick up a paperclip with a refrigerator magnet and defeat the gravitational pull of the entire Earth. And yet, it's also the most far-reaching, never switching off, never fading to zero, stretching its invisible fingers across infinity. That's why black holes, despite being compact, can influence each other long before they're anywhere close to colliding. The closer they get, the faster the dance becomes. Imagine two skaters on ice spinning toward each other. As their hands lock, they whirl faster, conserving angular momentum. The same principle plays out here, only the stage is space-time, and the skaters are so heavy they warp the rink itself. You can almost picture the fabric beneath them stretching, dipping, and quivering like an endless bedsheet. One mainstream fact: this slow spiral, technically called an in-spiral, doesn't just happen forever. Energy leaks away in the form of gravitational waves. Every orbit, every spin, every little twitch sends ripples outward. Like a couple waltzing on a wooden floor, their footsteps echo, carrying across the ballroom of the universe. It's these ripples that observatories on Earth have learned to listen for, the faint shivers in space-time itself. And here's a fun tidbit. The orbit of two black holes can start so wide that it would take longer than the age of the universe for them to meet. If that sounds like the world's slowest date, you're right. Some pairs may never make it to the final kiss, drifting forever in near-eternal circles. Scientists still argue whether interactions with nearby stars, gas, or even entire galaxies are the matchmakers that push them into each other's arms, or whether many such couples are doomed to endless courtship. You find yourself imagining the view: two black disks circling a common center, pulling at each other with tides strong enough to shred planets. Their orbital paths aren't neat lines but spirals, slowly tightening faster and faster, each revolution stealing a little time from the next. It's hypnotic, almost soothing, like watching a candle flame flicker closer to the wick's end. From where you drift, it looks inevitable, but it isn't. Not yet. The universe is patient, and gravity can play coy. 1,000,000 years, 1,000,000,000 years, what's the rush? For you, watching with a human heartbeat, it feels impossibly slow, but for them, bound by their colossal mass, this is destiny unfolding on the only clock that matters, the cosmic one. You realize, lying there under your blankets in the quiet of your own room, that gravity doesn't need drama to tell its story. It doesn't roar or flash. It whispers, tugs, coaxes. It persuades two invisible titans to lean in, closer and closer, until the whisper becomes a roar. And tonight, you get to drift alongside them, watching the opening steps of a dance that will one day shake the fabric of the cosmos. You feel the pull of their orbit tightening, the silence between them filling with invisible music. But to truly understand what's happening, you need Einstein, not the wild-haired caricature, but the equations he left behind, like cryptic sheet music for the cosmos. General relativity is the rulebook, and in it, mass and energy aren't just players, they're choreographers. They tell space how to curve, and space tells objects how to move. Simple, right? Except, simple in Einstein's world means the math looks like someone spilled alphabet soup across the chalkboard. At its heart, the idea is surprisingly intuitive. Imagine a trampoline stretched tight, toss a bowling ball onto it, and the surface dips. Now roll a marble across the fabric, and it curves around the dip, spiraling closer. That's gravity, except black holes are the cosmic equivalent of a bowling ball so heavy it rips through the trampoline entirely. The marble doesn't just circle, it risks being swallowed. And when two black holes share the same trampoline, the whole fabric shivers, curves, and folds in ways your brain resists picturing. Here's your mainstream fact. Einstein's field equations predict not just the attraction of masses, but the way space-time itself flexes and bends when those masses move. Without these equations, we'd think of black holes as vacuum cleaners, sucking things in, but relativity reframes them as architects of space, reshaping the stage as they dance. And the quirky tidbit, for decades, even Einstein doubted whether black holes, what he called singularities, could exist in reality. He saw them as mathematical oddities, like doodles in the margins of physics. Now, they're headline makers. Somewhere, if he could peek back, he'd probably mutter in German, "Well, that escalated quickly." Scientists still argue whether relativity is the final word. The theory has passed every test we've thrown at it, from predicting the bending of starlight to the ticking of GPS satellites. But at the edges inside black holes, or at the instant of their collision, Einstein's math stumbles. It describes a universe that curves into infinity, a place where our equations wave a white flag and surrender. Physicists debate whether quantum mechanics must swoop in to patch the gaps, or whether we need an entirely new theory, a quantum gravity we've yet to discover. As you float in this thought experiment, you picture two black holes moving closer. Their immense energy doesn't just bend space, it drags time itself into the whirl. If you could hover nearby with your watch, you'd see its hands crawl, seconds stretching like molasses. From far away, the black holes spiral in slow motion, but for them, everything races. It's a cosmic contradiction, both sluggish and furious, both inevitable and impossible to finish calculating. You sense how precarious it all feels. Equations scribbled on paper predicting the most violent events in the cosmos. And yet, they work. LIGO's detectors in Louisiana and Washington have measured the ripples these equations foretold a century ago. The numbers match the whispers of space-time, the notes of black holes colliding, the very tremors Einstein predicted while insisting the universe was too shy to reveal them. You settle deeper into the quiet, letting that irony sink in. Sometimes the universe hides behind math until it decides to hum a lullaby in the form of gravitational waves. And you, here, tonight, get to be part of the audience, watching the stage shift beneath two invisible giants, all because one man's scribbles still hold sway over the stars. You can almost hear it, the faintest tremor echoing through space-time, like a whisper that travelled across billions of light-years just to find you here, resting. These ripples are gravitational waves, and they are the quiet signatures of two black holes deciding to become one. It feels poetic, doesn't it? A cosmic event so violent it could shake galaxies, yet what reaches Earth is gentler than the shiver of a passing breeze. If your body were the detector, the stretch and squeeze would be smaller than the width of a proton. Imagine trying to notice your bedsheet shifting by less than the size of an atom while a cat is purring on your chest. Good luck with that. Here's the mainstream fact. When two massive objects orbit each other, Einstein's equations predict that they should lose energy not in light or heat, but in ripples of space-time itself. These waves travel outward at the speed of light, carrying with them a fingerprint of the collision. And yes, they really were detected for the first time in 2015 by LIGO. Before then, they were just beautiful math, like postcards we weren't sure had ever been sent. Now, every detection is like opening the mailbox and finding a note from the universe written in space-time. The quirky tidbit, the sound of two black holes merging if shifted into audio frequencies, is eerily like a chirp. Imagine the universe as a giant bird, whistling softly each time two cosmic giants collide. Scientists play these sounds at conferences, and honestly, it's a little surreal. You expect a thunderclap, but instead, it's a delicate whoop. Somewhere, the cosmos has a sense of humor. Scientists still argue whether gravitational waves can show us everything. The signals are faint, fleeting, and often buried in noise. Earthquakes, passing trucks, even a raccoon climbing on a detector can muddy the data. Physicists debate whether what we've captured is the full story, or if subtler patterns hidden in the ring down, the fading echo of the new black hole, might tell us something deeper about physics we haven't yet uncovered. You picture these waves spreading across the cosmos. They don't stop, they don't fade into nothing. Every ripple keeps going, like concentric rings from a pebble tossed into a pond, except the pond is space-time itself. By the time they reach Earth, the waves are unimaginably diluted, yet they still stretch detectors ever so slightly, arms 4 kilometers long, shifting by less than 1,000th the size of a proton. If that makes you feel inadequate about the stability of your hands when pouring coffee, well, join the club. As you drift deeper into this thought, you realize the poetry here. Massive black holes spiraling, colliding, and vanishing into one but the proof of their existence. The only reason we know the story happened is because space-time itself carries their memory. The universe is like a diary that writes itself, and gravitational waves are its ink. Every time you feel the hum of that idea, you're closer to the heartbeat of the cosmos. Picture this: two black holes caught in each other's gravity, bound together like dancers who can't stop circling, locked in a waltz that lasts longer than entire civilizations on Earth. This isn't a quick romance, it's a courtship that can stretch across billions of years. If you were to watch it in real time, you'd get bored long before anything exciting happened. Honestly, you'd probably fall asleep, wake up, live an entire life, and still they'd just be looping slowly around one another. Cosmic relationships really test the meaning of patience. Here's the straightforward science. When two black holes orbit, they gradually lose energy through gravitational waves. Each ripple steals just a little momentum, nudging the pair closer. But the loss is tiny. Imagine paying off a mountain of debt with pocket change. It works, but only if you've got eternity to spare. Most of the time, these black holes spin in circles so stable you could call them cosmic merry-go-rounds. The shrinking of their orbit, the in spiral, takes longer than the age of galaxies. A quirky tidbit? Some astronomers call this stage the gravitational wave background hum. It's thought that the universe is filled with countless black hole pairs humming softly in space-time, like a low choir you can't quite hear. If you had gravitational ears, you'd be surrounded by a cosmic lullaby, the combined music of billions of slow dances. Sadly, your human ears are stuck with crickets and traffic. Scientists still argue whether supermassive black holes, the ones millions of times heavier than the Sun, can actually merge within the lifespan of the universe. The problem is something called the final parsec problem. As the pair gets close, it's believed they may stall, unable to shed enough energy to take the last step toward union. Some think nearby stars and gas act as cosmic matchmakers, giving nudges that help the merger along. Others think many pairs may be stuck forever, orbiting without end. The debate is lively. Are we missing countless black hole unions because they simply never finish the dance? You imagine two black holes circling, not in the emptiness of space, but within the heart of a galaxy. Stars fly by like oblivious wedding guests, unaware of the slow approach. Clouds of gas twist around, sometimes falling in and feeding the black holes, other times just drifting past. Each encounter can shift the orbit slightly, like friends tugging two shy dancers closer together. But still, the dance remains slow, measured in eons. And yet, time is relative here. For us, billions of years sound impossibly long. For the black holes, locked in a rhythm written by space-time itself, it's just the natural pace of existence. Their patience is cosmic, their timing inevitable. They will merge, but not because of passion, not because of urgency. They merge because physics insists on it. The universe writes its love stories in equations, not sonnets. As the two black holes circle closer and closer, the dance that once stretched across billions of years begins to accelerate. From your cosmic vantage point, the difference is subtle at first, just a little less space between each orbit, a little more urgency in the curve of their paths. But physics has a way of speeding up when things get serious. At the brink of merger, time itself seems to twist into knots, like a fabric pulled so tight that threads begin to creak. This is the stage where everything you thought you understood about clocks and minutes and hours collapses into a strange blur. To a distant observer, the black holes seem to slow as they spiral together, their final orbits stretching toward eternity. From far away, you'd swear they never quite touch. Yet if you were foolish enough, recklessly foolish, to ride along on the edge of one of those black holes, you'd feel the exact opposite. To you, the final orbits would whip by at nearly the speed of light, each revolution like a heartbeat growing more frantic. Your time would feel perfectly normal, but you'd look out and see the universe rushing past in a dizzying blur. It's the ultimate relativity prank. Everyone's right, but no one agrees. Here's the grounded fact. As black holes close in, their gravitational wave signals spike. The waves grow sharper, louder, and faster, tracing out a pattern scientists call the chirp. It's exactly what it sounds like, a rising note that peaks just before collision. You could almost hum it, though your vocal cords would probably give up halfway through. Now for the quirky detail. Some researchers joke that, in theory, two merging black holes should sound like a cosmic boing if you could translate their waves into sound. Imagine the universe's most dramatic spring recoiling. It's a comforting thought, isn't it? Something so mind-bending, so terrifyingly powerful, reduced to the sound effect of a cartoon pogo stick. But here's where the debate rages. Scientists still argue whether we truly understand what happens to time at this brink. General relativity tells us one story, quantum theory whispers another. Some say the moment stretches forever from the outside. Others believe hidden physics must intervene, because infinities in equations usually signal that the math has gone off the rails. Is time genuinely shredded at the horizon? Or is it just our limited imagination collapsing under the weight of impossible numbers? That argument remains one of the deepest puzzles in all of physics. You watch the spiraling giants, and the atmosphere around them becomes chaotic. The space-time fabric doesn't just bend, it thrashes. Stars wandering too close would be hurled aside. gas clouds would be shredded and flung in luminous arcs. For the black holes, though, this is intimacy. They have danced for eons, and now they are so close that their horizons, those invisible boundaries beyond which nothing can escape, begin to brush against one another. There's no turning back. The tension is palpable. You can almost feel the universe holding its breath. The final parsec problem is over. There's no more stalling, no more endless loops. It's happening. Two cosmic abysses, each a monument to collapsed matter, are about to unite. And as they approach that edge, you realize this is as close as physics will let you get to witnessing the impossible. The moment of collision is unlike anything else the universe can stage. After billions of years of drifting, after eons of circling and tugging and chirping away energy in invisible ripples, the two black holes finally crash together. You might imagine it as an explosion, a thunderclap, a cinematic eruption of light and fire, but that would be too human of a story. The reality is quieter, stranger, and far more dramatic in its silence. When the horizons finally merge, there's no sound, no flash visible to the naked eye. If you were sitting in some impossibly safe seat nearby, and yes, that's a fantasy, no travel insurance would cover this trip, what you'd actually notice most is the way space-time itself convulses. It's not so much a crash as it is a blending, two invisible bubbles fusing into one. Their identities dissolve, their centers align, and the universe redraws the boundary. Now there is one black hole where there used to be two. Here's the straightforward fact. Simulations and detections confirm that the collision releases more energy in a fraction of a second than all the stars in the observable universe combined, shining together. That energy doesn't come as light, it comes as gravitational waves, the rolling thunder in the fabric of reality itself. And here's the quirky tidbit. Some theorists like to describe this final moment as a cosmic kiss. It's a ridiculous metaphor, of course. No roses, no violins, no candlelight. Just unimaginable violence, disguised as intimacy. Yet it's also not far off. The two black holes do meet, touch, and merge into something inseparable. A love story for objects that devour everything they touch. But here's the debate. Scientists still argue whether the very instant of merger is fully understood. General relativity gives us one clean picture, but only if you ignore quantum effects. At the scales and densities inside that brief instant, quantum mechanics insists it should play a role, yet no one knows how. Does the fabric of space-time remain smooth, or does it crinkle and fizz with tiny quantum eruptions? Does the new black hole instantly settle into perfect order, or does it briefly defy the rules before calming down? The answer remains hidden inside equations that refuse to cooperate. From your cosmic seat, though, you see the grand finale unfold. The last spiral turns into a plunge, the horizons collide, and then silence. A silence not of emptiness, but of completion. The dance is over, the duet resolved. In place of two restless giants, there is now one larger, calmer abyss, and space-time sighs and ripples that travel outward forever. You don't hear it with your ears, but your very bones would have quivered if you could translate those waves into sound. The universe has struck its loudest note in a key no human ear will ever hear directly. For a moment, you can almost believe the universe celebrates this union. Galaxies keep spinning, stars keep burning, but somewhere in the deep, a new black hole has been born not through collapse, but through embrace. And as bizarre as it sounds, you realize you've just witnessed a kind of creation. The new black hole doesn't simply sit quietly after swallowing its partner. It quivers, it trembles, it rings, though not in any way you'd recognize as ringing. This is space-time's version of a bell, one so vast that its vibrations ripple across the universe. Astronomers call this ring down, and it is the telltale sign that a newborn black hole is settling into its final form. Imagine striking a gong. At first, it wobbles with chaotic vibrations, deep, low notes, overtones you can't quite place, echoes that hang in the air. Then, slowly, the wobbling fades. The sound thins out into a pure, steady resonance until silence remains. A black hole does the same thing, except the ringing isn't carried through air. It's carried through the fabric of space-time itself. Each tremor is a gravitational wave. Each vibration is a signature of mass, spin, and shape, as though the black hole is humming its ID card across the cosmos. Here's your mainstream fact. These ring-down vibrations are so precise that, in principle, they could reveal if Einstein's theory is correct to the last decimal place. According to relativity, the final black hole must be perfectly described by just three numbers: its mass, its spin, and its electric charge, though in practice, astrophysical ones have almost no charge. This is called the no-hair theorem, the idea that black holes are bald, no distinguishing features beyond those numbers. The ring down is the universe's way of broadcasting those details. Now the quirky bit. Some researchers have joked about listening to these mergers as though they were music. In fact, when gravitational wave data is converted into audio frequencies, the final merger and ring down can sound like a brief, cosmic chirp. Some even say it's like the pluck of a bass string or the swoop of a video game laser. Imagine the death of two black holes rendered as a sound effect you could mistake for a retro arcade game. And here's where the debate comes in. Scientists still argue whether the ring down could reveal exotic physics beyond Einstein. If the new black hole has the slightest imperfection, some hidden structure, a deviation caused by quantum gravity, it should leave an imprint on the vibrations. Instead of a smooth fade-out, there could be echoes, tiny aftershocks that repeat at intervals, like a ghost of the collision replaying itself. Do those echoes exist? Observatories have hinted at them in noisy data, but nothing is confirmed. If they are real, they would rewrite everything we think we know about space-time. You, as the listener, picture it not in equations but in sensation. The newborn black hole rings with waves you cannot see, cannot hear, yet feel in the imagination. Ripples spreading like the aftershiver of a struck bell, carrying across galaxies, reaching even to the small blue dot where you sit. It's a lullaby and a roar at once, though only machines like LIGO and Virgo can catch it. For you, it is enough to know that every time two black holes unite, the universe briefly sings. You wouldn't know it just by looking at the night sky. Two black holes can crash together right now, halfway across the observable universe, and not a single star in your view would so much as blink. No flash of light, no exploding fireworks, just silence. That's why, for centuries, humans had no clue these mergers even existed. It took building machines of almost absurd sensitivity to finally hear what the universe had been whispering all along. That's where LIGO and Virgo enter the story. Imagine two enormous L-shaped tunnels, each arm stretching kilometers long, shining lasers back and forth with such precision that they can detect distortions thousands of times smaller than a proton. Yes, a proton, the little nugget inside every atom. You wiggle more in your sleep than these detectors allow. And yet, when a gravitational wave passes through Earth, it tugs the space-time beneath us just enough to nudge one laser beam ahead of the other. The result is the faintest interference pattern, a tiny mismatch that says, something out there just rang the cosmic bell. Here's your mainstream fact. In 2015, LIGO made history by detecting the first confirmed gravitational waves, proving Einstein right a century after he predicted them. The event came from two black holes merging about 1.3 billion light-years away. That's how far the signal travelled longer than life has existed on land here on Earth before softly jiggling our detectors. Now the quirky tidbit. The raw signal, when converted into audio, sounds like a little chirp. Not an ominous roar or a cosmic boom, just a quick whoop rising in pitch. If you weren't told it came from colliding black holes, you might mistake it for a bird call or your phone's notification tone. Humanity's first earful of black holes uniting. Basically the universe saying, ding. And here comes the debate. Scientists still argue whether these detectors could one day catch signs of new physics hiding in those chirps. Could echoes of exotic matter be buried under the noise? Might some hairy black hole betray Einstein's neat equations? LIGO and Virgo are powerful, but they are not perfect. Every blip they record must be separated from things like passing trucks, earthquakes, or even raccoons bumping into equipment. Yes, raccoons have caused false alarms. An entire team of world-class physicists held their breath over what turned out to be wildlife mischief. You picture it. Two arms of the Earth, listening like giant tuning forks, waiting for space-time's whispers. Every detection is another confirmation that black holes not only merge but sing their union across the universe. And with each new event, scientists refine their maps of the cosmos. They can trace how often galaxies collide, how massive stars die, and maybe even how fast the universe expands. For you, it feels almost tender, like eavesdropping on a conversation between two ancient giants, with LIGO and Virgo acting as our delicate stethoscopes pressed against the heartbeat of space-time. You don't see the black holes, but you hear their story, faint and fleeting, yet unmistakable. You picture galaxies as glittering cities of stars, each one bustling with billions of suns, clouds of gas, and dark matter scaffolding you can't see. Inside their crowded neighborhoods, black holes don't live in isolation. They are shaped, nudged, and sometimes shoved into encounters by the larger structures they call home. Galaxies, in a way, play matchmaker for black holes, though with less candlelight and more cataclysm. Consider this mainstream fact. When galaxies collide, their central supermassive black holes often get dragged toward one another by gravity and eventually merge. Our own Milky Way is on a slow-motion collision course with the Andromeda Galaxy, and scientists predict that in about 4 billion years, their central black holes, each millions of times more massive than the Sun, will spiral together. A cosmic wedding date, penciled in long before humans ever existed. Now here's your quirky tidbit. Simulations suggest that sometimes, when galaxies merge, one black hole doesn't stick around. Instead, gravitational slingshot effects can literally fling it out of the galaxy at thousands of kilometers per second. Imagine being a lone supermassive black hole, drifting through intergalactic space like the universe's ultimate runaway. If that's not the strangest third-wheel problem you've ever heard, I don't know what is. And as for debate, scientists still argue whether every galaxy has a supermassive black hole at its core. Observations strongly suggest it, but dwarf galaxies and some oddball systems complicate the picture. If not all galaxies play host, then not all collisions lead to unions, and the statistics of black hole mergers change dramatically. This question sits at the heart of understanding how common these events truly are. You imagine the choreography, entire galaxies merging, their spiral arms twisted into tidal bridges and streams of stars, while at the center, dark titans are drawn closer and closer. To you, it feels both grand and eerily personal, as if the universe itself has a quiet matchmaking instinct, bringing together its most mysterious residents across billions of years. The galaxies don't just collide, they arrange meetings that reshape the fabric of space-time itself. You've followed black holes through quiet pairings and galactic matchmaking, but sometimes the universe tosses in a twist worthy of a cosmic soap opera. Because while two black holes merging is already dramatic enough, what happens when three enter the picture or when one goes rogue? These exotic possibilities stretch imagination, theory, and observation to their limits. Here's the mainstream fact. Astronomers have detected triple black hole systems in a handful of galaxies. In these rare but real configurations, 3 supermassive black holes orbit in a gravitational tug-of-war. Simulations show that such systems are unstable. Eventually, one black hole often gets kicked out, while the other 2 tighten their orbit and merge. Think of it as the universe's version of 2's company, 3's a crowd, but with 1 trillion times the stakes. For the quirky tidbit, scientists predict that if a rogue black hole wanders through interstellar space, it could carry a cloak of stars or planets with it, gravitationally tethered like a bizarre caravan. Imagine an entire solar system silently drifting through the cosmic void, its sun enslaved to a black hole hitchhiker. Somewhere out there, such exiled systems may already exist, invisible until they pass close enough to reveal themselves by distorting starlight. It's the ultimate road trip you don't want to be part of. And then comes the debate. Scientists still argue whether these chaotic triple interactions could produce gravitational wave signals, strong and unique enough to be detected separately from ordinary mergers. Could LIGO or future detectors hear the frantic chirps of 3 bodies playing celestial pinball before 2 finally collide? Or would those signals be drowned in noise, leaving us only with the final, quieter story of the surviving pair? The question lingers, unsettled. As you picture it, the scene feels less like a peaceful dance and more like a cosmic mosh pit. Bodies flung, orbits twisted, trajectories rewritten. Yet, even in this chaos, patterns emerge. Mergers still happen, space still bends. The story continues, just in stranger, less predictable ways. You realize that the universe doesn't always follow the neat scripts we expect it improvises, and sometimes the improvisation is far more fascinating than the standard performance. You followed mergers through their elegant inevitabilities and their chaotic improvisations, but now you step with me right to the edge, the place where science holds its breath. Because even after a century of Einstein and decades of direct detections, black hole mergers still guard secrets that defy neat equations. Here's the firm ground. General relativity has predicted every gravitational wave we've measured so far. When LIGO announced the first detection in 2015, the waveform matched Einstein's math with eerie perfection. The inspiral, the merger, the ring down, it all aligned. On paper, the theory and reality seemed to shake hands across a century. But then comes the fog. For the quirky tidbit, some scientists propose that when two black holes merge, they might leave behind echoes that standard relativity can't explain, subtle ripples suggesting exotic physics, like quantum corrections at the event horizon. A few teams even claimed hints of these echoes buried in the data, though skeptics say they could just be noise. It's the universe's equivalent of a ghost story, but whispered in math instead of creaky floorboards. And here's the open debate. Scientists still argue whether classical general relativity will ultimately break down under the extreme densities of merging black holes. Is there a hidden quantum structure at the horizon? Do firewalls incinerate information before it can escape? Or do black holes have hair-subtle features that carry imprints of their past, violating the old no-hair theorem? Each possibility pokes at the boundary where gravity and quantum mechanics refuse to play nicely together. As you drift here, you sense the tension. On one side, the clean certainty of Einstein's equations. On the other, the messy suspicion that nature hides new rules just beyond our instrument's reach. It's a liminal space, like standing at a coastline at night, hearing waves but not seeing where the land ends. You're aware that every merger detected brings us closer to either confirming Einstein forever or finally catching him blinking. And so, at the edge of understanding, you realize the story of merging black holes isn't finished. It's still being written, wave by wave, by detectors on Earth and by the restless imagination of the scientists who refuse to stop asking questions. You might wonder, why should you, lying here tonight with your pillow and your blanket, care whether two black holes somewhere out there are smashing together? They're distant, invisible, and definitely not popping up in your backyard, though wouldn't that make the news cycle lively? Yet the ripples they send through the universe eventually reach your life in surprising, practical ways. Take GPS, for example. The satellites guiding your morning commute or your midnight snack run, no judgment must account for both special and general relativity. Their onboard clocks tick differently because of their speed and their height above Earth's gravity. The precision required is astonishing. If engineers ignored relativity, your GPS would drift by kilometers every day. And where did the framework for those corrections come from? The same Einsteinian equations that predict how black holes merge. So, when you ask your phone for directions, you're leaning on math designed to understand cosmic monsters. Then there's the broader story of cosmic history. Black hole mergers give us a direct glimpse into how galaxies grow. Imagine galaxies as social matchmakers, tossing their central black holes into dance after dance until two finally collide. By listening to these events, astronomers can trace how structures like our Milky Way were assembled. In a sense, every merger is a page from the family album of the cosmos. And here's a quirky tidbit. Some researchers speculate that the energy released in mergers could one day serve as a background hum, against which entirely new physics might be measured. Like using thunder to detect the whisper of a breeze, these colossal crashes might help reveal subtle distortions in spacetime we haven't even imagined yet. Of course, scientists still argue whether these observations will ever bridge the gulf between general relativity and quantum mechanics. Will mergers give us the first hard evidence of quantum gravity, or will they forever remain giant, silent affirmations of Einstein's already dazzling theory? Nobody knows, and that uncertainty is what makes each new detection feel like a fresh secret from the universe. So, yes, whether it's the phone in your hand, the history of your galaxy, or the deepest puzzles of physics, black hole unions matter more than you might think. They're not just faraway fireworks. They're part of the reason your world makes sense at all. When two black holes become one, it's not just an event, it's a story stitched into the fabric of the cosmos. You've followed the quiet attraction, the patient spirals, the sudden crash, and the ringing aftermath. But if you look closely, the narrative doesn't end with a merger. It only deepens, whispering about time itself, about endings that turn into beginnings, about how the universe keeps reinventing itself. Black holes have always carried the flavor of finality. They swallow matter, erase light, and seem to mark the ultimate full stop in nature's grammar. But when they merge, they don't just consume, they create. A new black hole forms, larger and more powerful, born out of destruction. In a way, it's a rebirth, a reminder that even in the deepest silence, something new can take shape. This is where the story begins to edge into philosophy. If the cosmos can recycle, collapse into creation, what does that say about time? Is it a straight line toward entropy, or a looping thread that folds upon itself? Scientists still argue whether the universe will one day fizzle into a frozen stillness, collapse in on itself, or spin off into endless cycles. The evidence from black hole mergers suggests that endings are rarely the end. Here's a quirky thought. Some physicists propose that information falling into a black hole isn't lost forever, but scrambled, encoded, and maybe, someday, recoverable. Like cosmic graffiti on the walls of space-time, nothing ever truly vanishes. And if that's true, then every black hole merger is not just erasing a past, but also archiving it in ways we barely understand. The ultimate question is this: why do these stories matter to you here, listening in the quiet of your night? Because they mirror your own thread in space-time. Just as galaxies collide and weave new structures, your life too is a series of mergers of moments, choices, and memories that reshape who you are. Black holes may seem remote, but their dance is a reflection of the same truth, that time carries us forward, that transformation is inevitable, and that endings can hold the seeds of beginnings. So tonight, as you drift towards sleep, you can carry with you the thought that somewhere, perhaps right now, two colossal shadows are colliding. Their story ripples across space-time, subtle but real, eventually brushing across your life in the most ordinary of ways. You are connected to them, not just an observer, but a participant in the same cosmic play. And just like them, you are both the echo of everything before and the seed of everything to come. Now the journey softens. The collisions, the spirals, the grand equations, they can all rest for a while, like stars dimming at the close of a long night. What remains is the quiet sense that you are part of something vast, that even the most unimaginable forces in the universe share a rhythm with your own heartbeat. As you breathe slowly, picture the universe not as a cold, distant void, but as a living tapestry. Black holes merge, galaxies drift, stars flare and fade, and yet all of it happens in the same shared silence that surrounds you now. In this moment, you are not apart from the cosmos, you are woven into it. Every cell in your body is stardust, every breath a recycled gift from ancient stars. There's no need to hold on tightly to these ideas. Let them drift, as softly as your thoughts do when sleep comes closer. Perhaps you'll dream of spirals and galaxies, or perhaps of nothing at all, just a deep, restful dark, like the heart of space itself. The universe is wide, mysterious, and endlessly surprising. But here, in this quiet night, it is also simple. It is enough to know that you are part of it, that its story is also your story, and that in the gentle flow of time, there is room for peace. So close your eyes, let the silence settle in, and allow yourself to drift, knowing that somewhere far away, the universe continues its patient dance. And tomorrow, when you wake, it will still be there, vast, ancient, and waiting for you to look up again.